Hi, so this is a video presenting some exercises I've prepared. This is mostly for preparing for the exam. So there's going to be very similar questions in the exam at the end. I'm going to be talking more details about the exam when I present to a video about the last lecture, the review lecture. That's basically going to go over all the material that we've covered and then highlighting some of the material that you may expect to have some questions on this material. I'm gonna also give you a sample exam that I had in the past years, so that you can have an idea of what questions to expect and then prepare for the exam. So if you want to have more details about that, you should look at the video about the last lecture in the schedule. So let me share the screen here. So this is the slides. So this slides you can find here, exercises. So these are the slides. It's going to be this very video here that's going to be posted here. And then for the lecture, the last lecture I was just referring to, this is the last lecture describing, what is the all the material we've covered, and then pointing out some likely questions that you may have in the exam. So I'm going to make this video a little bit later on today, and then you'll be able to see this video here. So let's get on with the slides. So the slides, I've already downloaded them here. So let's put it on full screen. Let's put up a nice pointer here. Okay. So essentially, this is divided in two parts. Go to the end here. There's some nice references I've created. So, okay. So there's essentially exercises for lexical analysis and syntactical analysis. The main idea of these exercises for lexical analysis is, when we covered here, if you click here, this is a link to the slides where material that we saw in class is being covered, which is the topic of the exercises that you will find in these slides. So if you want to refer to the material in question, you basically click on any of these here. This is for lexical analysis slides, and this is for the syntactical analysis slides. For lexical analysis is essentially, so you get a regular expression, and then you generate an NDFA from the regular expressions using Thompson's construction, and then eventually you use the Rabin-Scott powerset construction in order to create a DFA from the NDFA. Luckily, we have some tools online. So for example, if you use this tool here, if you click on this link here, it's going to bring you to a tool that basically allows you to put a regular expression in input and then click, and then it basically gives you an NDFA and then eventually a DFA. That's basically what I used to demonstrate the exercises during the slides. For the syntactical analysis, so basically what I'm having as exercises here is given a certain grammar, generate the SLR table, the CLR table or LR1 table, and so SLR, CLR, and LALR. So that's basically exercises showing the result of applying the material again that we've covered in class here. Okay, so I've verified that these exercises I've chosen comply with the method that I've shown in class. So let's go back to the beginning. Okay, so first there's two exercises on lexical analysis part. So basically here we have some lexical specifications. We generate a regular expression, and from this regular expression we generate an NDFA using Thompson's construction, and then using Rabin-Scott powerset construction we generate a DFA. Here's the first example. So very typical when you have programming language lexical specifications, you have a list of tokens. So some of the tokens are pretty standard, don't require a definition, but some of them might actually require some kind of grammar or mini grammar describing what is the nature of certain tokens. For example, an identifier might be a letter followed by any number of letter or digit. These are very simple descriptions. For example, number is any number of digit. So that, for example, excludes more complex things such as floating point number or excluding leading zeros for an integer and so on. So of course, the examples are kept as simple as possible in these exercises, because of course, the more you make it more complex, then the more the graph, the NDFA, particularly the NDFA, becomes larger. So I kept the examples simple. And of course, you can expect that when you have the exam questions, that it's not going to be a huge, I'm not going to ask you to generate a huge NDFA or so on and so forth. So I want to basically see that you know what is the procedure involved in creating, for example, an NDFA from the regular expressions using Thompson's construction. In the exercises here, I'm not showing all the steps, but eventually in the exam, I might be asking you the steps, because I don't want, in the exam, I want to see that you know how to do these things. Here I'm basically showing you the results for some examples using the tools. So in the exam, you'll be allowed to actually use the tools online. So basically, you're gonna take the question I provide you in the exam. For example, generate the regular expression from the token list definition that I'm giving you. Then you take this regular expression, put it into the tool. At least you'll have the correct answer. But then I might be asking you to provide me the steps involved. And the tool does not provide you with the steps. So the tool is going to help you to get the correct answer, and it's going to be up to you to provide me with the steps as an answer to the question. Okay, so if you basically take this definition or lexical specification in input, then you can generate this nice regular expression here. So basically, it is lesser or greater or equal or less or equal or letter followed by letter or digit or any number of letter digits. Or, so that's basically this definition here that you've put here. And then for number, so that's basically digit star. And then this is for a comment. Comment is essentially percentage mark at the beginning, at the end, and then in the middle you have any number of letter or digits. That's basically here that you translate somehow into a regular expression. Why am I using this specific format for regular expressions? Because there might be different tools that would have their different format for regular expressions. That's basically the format that is used by this tool here. Okay, so depending if you're using another tool, then the regular expression might be a little bit different. Okay, so if you use this tool here, so you basically, well, let's try to do it. Now, how do I? Yeah. Okay. So if I go back to my example here, I click on this here. It's going to bring me to this tool. I go back here and copy this here, which is my regular expression and the specific format for this tool. Then I copy my regular expression here. I go convert. And basically, it's generating me an NDFA. So that's the transition table for this NDFA. And this is my NDFA here. No, that's actually a DFA. If I click, so that's basically by default, it generates the DFA. If you want to see the NDFA, then you click on NFA here. And basically it is providing you with the NDFA. So you see that you have these epsilon transitions here. So this is the branch for greater or equal, lesser or equal, equal, equal. And this is the branch here for letter followed by any number of letter or digit or a single letter. So you see, okay, so this is the result, basically the resulting graph or NDFA that you would get if you would apply Thompson's construction. Then if you want later on to have the DFA, and you click here, that's basically providing you with the DFA. Here you have the table, the transition table for the DFA, and here is your DFA. That is basically the result of taking the NDFA that you had before, applying Rabin-Scott powerset construction, and you actually get the DFA. So you see that even gives you what are the sets of states that corresponds, the set of states in the NDFA that correspond to the states in the DFA, just like as Rabin-Scott powerset construction is doing, which we've covered in class in slide set number 2, I believe. Okay, so that's it for this first example. So as we just saw, so you see here that we have the resulting NDFA. So that's basically a screenshot of what we just saw when we applied the tool, when we used the tool. This is again a screenshot of the resulting NDFA if you apply Rabin-Scott powerset construction. And this is the graph representation of this DFA. Now I have created another example. This example is more, I would say, abstract and also resulting in a larger graph. So here you see that your lexical specification, well, of course, it's not very programming language-like example, but yet this is some kind of mini grammar that is describing what might be understood as being a lexical specification for a language, which is expressed using some kind of hybrid between a grammar and some regular expressions. So if you have this in input, then what you need to do is to create one large regular expression, just like when we had in the previous example. Basically, we took this specification, which included these definitions here, and we created one regular expression, okay, with basically or. And for each of the things which are defined here, you create one single regular sub-regular expression using the definitions here. Basically, you're doing substitution here. Each of the branches is a sub-regular expression. So eventually, if you have an input like this as your lexical specification, then what you need to do is to figure out the sub-regular expressions for each of the non-terminals that you have here. So for example, if you have C, then the regular expression that corresponds to this is essentially this one here. And if you have B, then B, as you may note, is using C. So that's basically B followed by either H or C, which is defined here. So basically substituted C by its definition inside of this regular expression here. And all of this is followed by C and an or F. So you see that you have two rules for B, so it's either this or that. Okay. Basically, I substituted any non-terminal that I had in the definition of B inside of the regular expression that I'm generating. And you do the same for A, which basically A is B followed by D. So you basically take this B here and you say A is B followed by D. And more complicated is you generate the final starting symbol regular expression, and you basically substitute. So you have S followed by either A, which is this here, which is followed by I, or B star, which is, this is B and then star, or B. So basically you generate the sub-regular expressions and you substitute them, and basically you come up with a single regular expression in the end, and that's basically what you input inside of this tool as I've shown before, and then you would get this gigantic NDFA. So if you follow, for example, this is each of the branches that correspond to each of these rules here. So you start here, it's either you go here or you go here, and so on and so forth, okay? So this is your, basically if you use Thompson's construction on this regular expression here, you would eventually come up with this pretty large graph. So I'm not gonna ask you to have such a, let's say, a large example for an exam question. You know, there's going to be a lot of questions on the exam, so it's going to be more smallish, smaller example, smaller exercises than this one, definitely. But this one is a good exercise because, you know, there's also the exercise of doing the substitution and creating the regular expression. But if you want to do Thompson's construction on this expression, this regular expression here, you'll find that there's a lot of steps involved. So let's just say that I might ask you to create the regular expression for an example like this, but I'm not going to ask you to, you know, spend a lot of time doing an NDFA out of a very large regular expression like this here. But this is a good exercise if you want to practice for the exam. Then, of course, if you apply the Rabin-Scott powerset construction on this NDFA, then you would come up with a DFA like so. You see that if you try to apply Rabin-Scott powerset construction on this, you'll see that it's going to be extremely long. Okay. Not that I'm going to ask you a long example such as this one for the exam, but it's good to see larger examples. And that would eventually result in a DFA like this. Note that in the tool, it asks you, it provides you with a tool to do an optimize DFA. As we didn't see that in class, how to provide an optimize or to calculate, to compute an optimized DFA. This is not going to be part of the exam. The questions that will be in the exam are only about what we covered in class. If you look in the references at the end of the slide set here, you will see references to the slides that we covered in class. All the questions are going to be about things we covered in class. Only about things we covered in class. Okay, so this was the examples for the lexical analysis. So here are some examples or exercises about syntactical analysis. So these exercises are basically about how to generate parsing tables, either for top-down predictive parsing or bottom-up parsing. So that's basically, again, the only parsing methods that we saw in class and that I explained during the lectures. So this is actually using this tool here, which is called the context-free grammar checker. So if I may go back here, because this doesn't work if I'm in the presentation mode. So example, if you go here, click on this here. So it's bringing you to this tool, very nice tool, designed by people at University of Calgary. So if you get here, so basically you can enter your grammar here. So you have example grammars. For example, you can take this one here, and then you can copy this grammar. Is this working like this? Okay. Oh yeah, okay, so let's take this one, and for example, you can generate the SLR table for this grammar. So it just basically generates the table and then presents you with the graphs. You have the item sets and so on. So again, this tool shows you the result. It doesn't show you the procedure involved, for example, in creating the item sets. Okay. So very likely it is that in the exam, I'm going to ask you to show me the procedure to actually come up with these item sets. Okay. So again, don't expect it's going to be a very large example. So that particular example is a good size for me to ask for an exam. You know, I can't expect that you're going to have to create the table for a real programming language, such as we had in the project, which has literally dozens or maybe 100 states. Not going to ask you a question like this, of course. So this is a good example of what you can expect as a size of a question that you may get in the exam. Okay, let's go back here. So for each of the examples, I created a link that you can click that basically brings you to a particular example. Because the thing is, if you, I've shown that before, sorry about that. Okay. So if I go back here, yeah, I go here, you will see, you may see that there are example grammars here. There's plenty of grammars here. So I have selected some that I've checked, and that if you apply the methods as I'm explaining them in class, I explain in class following the lectures, there is some results. If you click on any of these here, there is some results that I found that there were differences in the results. There are some grammars. If you use the same exact technique I've shown in class, there are some of these grammars or results that are not the same. I was not able to, so I literally chose some examples, which I put in the slides, for which the results are the same. Okay. So all this to say that there's plenty of examples here if you want to exercise using this or see more examples. So feel free to, for example, go here. Here you have, oh, this is an interesting one. So you have an interesting grammar here, and then you can actually generate, for example, the SLR table. You see, this grammar looks interesting, but it actually is generating an enormous, well, a small, for a programming language, that's a small table. But again, this example seems interesting, but I'm not going to ask you a question like this in the exam. Okay. It's an interesting example, but it's too long for an exam. Okay, for an exam question. So let's go back to this here. So, okay, so let's take this cute little grammar here. And then if you actually use the tool, then it's going to tell you, well, let's go to this particular one. So, okay, so here is this grammar, and then, for example, you generate the LL1 table. Basically, if you see, when you generate the table, if you see some red, things that are in red, that's basically meaning that there are some conflicts. If you remember, there is a procedure that I've shown in class as to how to generate the table. There's some kind of heuristics that you have to apply, some procedure that you have to apply with some rules and so on. Basically go over all, I'm not going to go over this procedure inside of this lecture today. So it's up to you to review what we covered in class. So all this to say that if you go to the slide set, okay, let's go to. So in this case, if you want to generate the LL1 table, that will be in this lecture here. So if you go in this lecture, it's gonna show what is I've shown in class about how to generate an LL table or LL1 table or top-down parsing, table-driven parsing method, how to take a grammar and generate an LL1 parsing table. So if you want to know the steps involved and so on, you have to follow the steps I've explained in this slide set here. So all this to say, if you take this grammar here, take the slides, and you follow the procedure I've shown in class, you should come up with this here. You may remember that many grammars actually cannot be parsed using the LL1 method. For example, if you have left recursion, it doesn't work. You can actually try, if you have a grammar that has left recursion, you can try to apply the method. What's eventually going to happen is that there's going to be some of the cells in the table, you're going to want to insert two different things in the cells, because you may have a first conflict or a first follow conflict. Okay, and then you would have to transform the grammar. Possibly you can transform it into an LL1 grammar, in which case you're going to be able to generate the table. And then if you use this tool, nothing is going to be read in this table. Eventually we'll come up with some examples that have some red in it. So all this to say, if you apply the method we saw in class in the slides that I just shown, and you apply this on this grammar here, you're going to find this table. So if we go back. Okay. So using the tool, we're able to find that for this particular grammar, this grammar is LL1. So there's no red in the table. There's no conflicts versus LL1 methods for this grammar. It is also an SLR grammar or SLR1 grammar. It is also an LR1 grammar, which is equivalent to what I refer to in the slide as CLR. And it is also an LALR grammar. So basically here is the grammar. The tool provides you with some statistics or facts about the grammar. It gives you the first and follow sets of the grammar. So if you want to practice using to compute first and follow sets, which is a very, of course, a very typical question that you have in an exam. In one of my exams for this course, computing the first follow sets given a grammar. So this tool can help you if you want to practice this. And then it also determines whether some of the non-terminals are nullable or endable. It also computes whether the non-terminals are reachable and realizable. If you want to have some definitions, these are not concepts we covered in class, like what is reachable, realizable. If you make a Google search, you'll actually come up with some very nice definition given by the people that designed this tool at the University of Calgary. Very well done tool. There's also, if you see at the end of the slides, there's also this Gramophone. That's basically the tool I'm using. Context-free grammar checker. This is a link basically to the example grammars, a table with all the different kinds of grammars. So that's a link to that. Also, I found another tool, which is kind of a spin-off to this tool, which is called Gramophone. It's interesting because it's a GitHub repository. So one of my concerns here is that this tool here is an online tool, so it's likely that it might disappear at some point. That's why I was trying to find other tools, and I actually found this Gramophone tool, which is spin-off of this context-free grammar checker. It's a little bit different. It doesn't provide as many features, but it's doing jobs very similar to this other tool here. There's also this CF grammar tool. What is interesting about this one is that it enables you to have, well, let's check it. What's interesting with this one here, you enter, for example, a grammar, you have a, let's say XB, and you enter another one, and then you say, for example, X is X followed by X. And then, of course, I need here to enter a nullable part or epsilon. So you see that it actually provides you with samples of strings that can be generated by this grammar. Okay. Well, as for many tools, one of the particularities of using tools like this is that you see that, for example, you might say, oh, I could have in the project could have entered my grammar in this tool and so on, but there's a lot of restrictions to many of these tools. Like, for example, what's the format that you have to use? In our project, we had some non-terminal symbols, like, for example, statement. But of course, here, the problem is that if you try to enter statement, that you can't have names for non-terminals that are more than one character. Okay. So many of these tools have particularities like this, which is actually greatly limiting what you can do, how you can use them. So it's a very nice tool, but it has its own restrictions and how, what's a valid grammar that you can use. But what I found very interesting about this one is, for example, let's say you enter the string here, then you can put the string here, and then it tells you whether this is a valid string. Of course, I could took it in the list of valid string here in the language, but what's really interesting here is that you can see the derivation. So how did you, what are the rules that you can use to actually, in a sequence, to actually generate this here? So basically, it provides you with all the derivation steps. This would be here a rightmost derivation. It doesn't provide you with either rightmost or leftmost, but that's a good start. Okay, so that's yet another tool. There's plenty of tools that I found, but these are the ones I put out here in this slide set. So let's go back. Okay. So we found that this grammar is LL1. There ain't no red here. So that means basically if we use the method I've shown in class, how to generate an LL1 table for this grammar, you should come up with this result. Okay. Again, this is showing you the result. In an exam question, I might ask you to show me the procedure to actually come up with the table. So that's why if you use this to actually do some practice, you should do it by hand and try to come up with the result. And it's not only about showing the result, because of course this is an online exam. So if I'm asking you, give me the LL table for a particular grammar, then if you know how to use this tool, you're basically going to take my question, put it in this tool, you get the LL table, copy, paste, and here's my answer. That doesn't tell me that you understand how to do it. Okay. This tool is going to give you the right answer. That's a very good start. So again, important to know how to actually achieve that. So for the same grammar, we actually can see if this grammar is SLR1 and what's the result of the SLR1 table. So this is the resulting table. You see that there ain't no red in this table, that means this is a valid SLR1 grammar, and that's the state transition diagram that actually shows what are the item sets for each of the states. Okay. Very typical question is that I'm asking you to provide the item sets for the resulting data flow, the resulting graph when you actually are generating a bottom-up parser out of a grammar. If we continue further, then here we find, if we're trying to generate the LR1 or CLR table, then you're gonna come up with this result here. And then this is the CLR or LR1 item sets for each of the states. Then the next step is to see what would be the resulting LALR item sets. Again, if you want to remind yourself how to do that, please go to the corresponding lectures that I gave earlier in the semester. So the idea, roughly speaking, if you want to generate LALR, then what you need to do, there's other ways to do it, but how I shown in class is you basically come up with the CLR item sets, and then you try to see if some item sets for different states are basically the same item sets, and then you merge these states. Again, there's other ways to do that. That's what I shown in class, and that's what I'm gonna expect that you know how to do in the exam. Fact of the matter here is that if you look at all the states and all the item sets of all the states, you'll see that there's no two states that have the same item sets. So basically that means the LALR table and the LR1 table is the same. So that's an example of that. Here's another example. So I tried to find different examples that were first were compliant, that the tool results in the same result as the method I've shown in class would be generating. Second, I tried to find some different examples. For example, this grammar here is LL1, but it's not SLR1. It is LALR1 and LR1. So basically, it is everything, but it's not SLR. So if we look at the LL1, so that's basically the result for this. And what I want to show you here is that you have some red here. So basically that means you have a conflict. So for example, here, this is a reduce operation. So if you apply the method I've shown in class, then you're going to analyze your grammar, and then depending on particular situations, you will want to insert a reduce action into the table. Now, what's happening with this grammar is if you look in state 2, then you have these two items here are terminal items. Okay. The dot is at the end of the right-hand side. So what's happening in these cases, if you remember, then you're trying to add a reduce action into the table in state number 2. Thing is that here, because you have these two terminal items here, which have on their left-hand side two different non-terminal symbols, so you're going to want to insert two different reduce actions. So there's a reduce conflict in this state for the for this particular grammar for the SLR method. So basically, you cannot use SLR method to construct a parser for this grammar. So if we go to LR1 and LALR1, so if you construct the table for LR1, then you're going to come up with these item sets, and then you're going to come up with this table. Again, here, if we look at the item sets for each of the states, you find that there is no two different states that have the same item sets. So LALR1 is the same as LR1 in this case. Go forward to another example. So here, that's another example, shorter example, for which this grammar is compliant, I might say, with all the methods we saw in class. So it is LL1, it is SLR1, it is CLR, and it is LALR. So this is the kind of example you can actually see, hope to see as a question in the exam. You know, it's short. If I'm asking you a short question like this, I'm going to expect that you show me all the details of how, for example, you came up with this table here. Okay. So same thing for SLR1. So basically, this is the item sets in the exam. I would be asking you to provide me with this graph and the item sets, but also I would expect that you show the procedure involved in generating the item sets. And then you see here that, again, in this case, there is no two states that have the same item sets. So there's basically LALR1 is the same as LR1. Let's go to another example. This one is LL1. It is not SLR1. It is not LALR1, and it is actually CLR or LR1. So this is the parsing table for the LL1 or top-down table-driven parsing. This one here. This is the SLR, and then you see again, there is, if you see, for example, state 7 is here. So you have a reduce problem here with your state number 7, because again here you have two terminal items which have two different non-terminals on the left-hand side of the prediction. Okay. So if you construct, however, the CLR or LR1 table, then you're going to come up with these item sets and then this corresponding table. However, if you're trying to generate the LR1 table, then you'll realize that as you're merging item sets, it's actually creating a conflict. Okay, well, that's an interesting example because it shows you that even though you might have a correct or valid LL1 item sets, when you're trying to merge some of the item sets, then it might actually create a conflict. Here's another example here. So this basically is LL1, it's not SLR, and it is LALR and LR. So here's again, this is an example that is what the kind of magnitude of example that you should expect for the exam. Here, if you're trying to do the SLR method here, you'll see that there is reduce conflicts in many places in state 0, state 5, and state 9. So state 0, you see that you have these two terminal items on the left-hand side, you have two different non-terminal symbols. In state 5, you actually have the same, and in state 9, you actually have the same. The problem here is that you have this terminal item here, or not item, but you have this epsilon rule here, you have this epsilon rule here, and you have var that starts this one here, and that's why it results in having this reduce conflict. Okay, so, but you see that it is not SLR, but if you use a more powerful method, which is CLR, then you can actually generate the item sets. Why? Because it's using look-aheads, which SLR is not. So it make it, a discrimination between things because, or by using the look-ahead sets. That's a good example here because you may see that if you generate the CLR or LL1 parsing table, you come up with this, and you come up with these item sets, and eventually you can find that there is some states that are the same, and eventually if you merge these states together, then you come up with this somewhat smaller table. So you see that this one had 17 states, and then when you merge the states that have the same item sets, you come up with only 11 states. That's actually what is the power, the real power of the LALR method, is that it is almost as powerful as CLR or LR1 method, but it allows you to generate tables which are smaller, which used to be, back in the day when it was invented, very important. Okay. It's not necessarily nowadays that much important because of the amount of memory that our computers have, but somehow it makes the compiler or the parser run faster if somehow the table is slower, especially for the parser generation. But again, here, considering the power of computers we have now, it's not as important as it used to be in the 1960s, for example. Okay, so that's about it for that. So again, I reemphasize, this was exercises that I'm presenting here. It's showing the results. It's not showing the procedure in an exam question. I'm going to ask you to show me some kind of trace describing the procedure that you use to actually achieve the result. So that's basically giving you showing you how to use tools to actually compute the result, so that when you do some exercises, you at least see what is the correct answer to your questions, right, to the questions that you may have. Plus, in the exam, you also have access to these tools. So as I'm giving you the questions in the exam, you're going to be allowed to go use these tools and find the correct answer. Of course, then I'm going to be expecting that you're going to provide me with some kind of trace of the procedure that you used to achieve this result. I'm going to provide with some more details about the content of the exam in an upcoming lecture that I'm going to post later today. So if we go back here, so the review and discussion on final examination. So the slides are here, slides have been done, updated. So I'm going to create a video here giving more verbal explanations about that later today. So that's about it for this lecture. So see you around.